Okay, good morning. Yeah, as I said to be in the first lecture, this class content will have three kind of like major topics, like time complexity, which we talked a little bit about, circuit complexity, and randomness. So today's lecture will be a bit of a review and a bit of new stuff about probabilistic complexity classes. Then on Thursday, we're going to have like a somewhat technical lecture on the Cook-Levin theorem and very efficient versions of the Cook-Levin theorem. And then I sort of feel that the class like really starts next week. I mean, that's when I feel kind of got over a lot of like the groundwork and like we can start doing some cool new things. But this stuff is also cool. Probabilistic complexity classes are extremely interesting. Okay, so let's remember probabilistic Turing machine. You know, it's just like a normal Turing machine, except that basically you think it can flip random coins. And we'll take a model where it flips like a 50-50 coin at each step. Formally, you can let it have like two transition functions, and it chooses randomly at each step which one to use. An equivalent way of looking at it, which we'll often do, is to think of deterministic Turing machines, which have two inputs, the real input, x. So we're going to use this notation here. M of x r, this is like the real inputs. And r is like a random string. That can be like, you know, of length equal to the running time of m or infinite if you like. That's also, it's read once. So like, you know, you can process it left to right. You can remember the random bits if you want to write them down on your scratch tape, but otherwise you can just read them. Okay, and we assume that they're like filled with independent random bits. So these are the equivalent models of probabilistic Turing machines. And another thing to remember in the definition is that the running time, there's a couple of different ways you could define the running time of a probabilistic Turing machine on an input x. You know, is it the expected running time or what? We're just going to take the simplest definition, which all the definitions, it doesn't really matter which one you take, so we'll take one that's simple for us. We define it to be the maximum running time over all random coins r. So if you want to say you have a probabilistic algorithm that runs in time n squared, then on all length n inputs, it should be the case that it takes at most n squared steps, like regardless of how the coins turn out. It's not really a big deal, right? Because if let's say it works most of the time in n squared steps, then the algorithm can like keep a clock, and like once its running time has gone past n squared, it can just decide to stop and fail. Okay. So let's describe or define some probabilistic complexity classes. So I'll start with maybe the most simple and basic one called BPP. So language L is in the complexity class BPP. The last P stands for polynomial time. The second P stands for, the middle one stands for probabilistic. And B stands for bounded error. If there exists a polytime probabilistic Turing machine, M, such that two things hold. So first of all, on strings that are in the language, the machine should accept with quote unquote high probability. And let's say that means at least 2/3. And here the probability, I'll write it like this. It's over the coins or the random bits r that m uses. And on the other hand, if x is not in L, and the probability that m of x accepts should be small. Let's say at most 1/3. This 2/3 and 1/3 look a little bit funny. They're like explicit constants to build into the definition. We'll see, or you'll be reminded shortly that it doesn't really matter if you change these constants to other ones, as long as they're bounded away from each other, and from 0 and 1, you'll get the same class BPP. Yep.
Does the first line imply the second one?
Nope. So like you could, and we'll talk about this later. It's a funny thing about BPP. You might have a probabilistic Turing machine that on some strings x accepts with probability half. If that's the case, then that Turing machine M does not define a language in BPP. Okay? A language in BPP is only defined when your Turing machine M has a somewhat special property, which is actually can sometimes be hard to reason about, that on every string either it accepts with high probability, at least 2/3, or it accepts with like low probability, at most 1/3. Okay, and let me also emphasize that this is a worst case statement over inputs. So we're never going to talk about like what happens on a random input. We're always going to talk about like you have a guarantee for every single x. Your algorithm succeeds, it gives the correct answer with high probability, where the probability is only over the algorithm's internal randomness. Okay, one could equally describe this as just saying on every input x, M gives the correct answer with probability at least 2/3. Okay, and more generally, you can define, I think I won't write it very carefully. You can define BP time T of n. Okay, so this is the version where the running time is polynomial, but for any fixed time bound, you can define BP time, this class of languages, things that can be decided with error at most 1/3 and time T of n. All right, now let me put this in a bit of a box here. I'm going to spend quite a bit of time thinking about what happens if we vary these two parameters, 2/3 and 1/3, because they look a little bit arbitrary right now. Let me make a little table. So what happens in this definition if you change greater than or equal to 2/3 and less than or equal to 1/3, on the two lines, to something else? What complexity class do you get? So the first thing I told you is just by definition, if you put 2/3 here and 1/3 here, that's BPP. So I'll tell you as a fact, hopefully you've seen it before. Let's say you said, well, I don't know why they chose 2/3, like 1/3 chance of error. What if we chose at least 3/4 and at most 1/4? In other words, the machine should get the right answer except with probability at most 1/4. Well, it looks formally different, but you get the same class. This also equivalently defines BPP. And we'll see why later in the class. But basically, if you have an algorithm that gives the right answer except with error 1/3, and you run it a few times independently and take the majority result, that will boost your probability of correctness, or it'll reduce the probability of error. And with a few runs, you can make that probability of error go down to any small amount, like 1/4 or 1%, or we'll see even more possibilities. And therefore, a 1/3 erring algorithm can easily be transformed at a constant factor runtime blow up to a 1/4 erring algorithm. So in particular, to generalize this a little, actually, if we put 1 minus epsilon and epsilon here, for any fixed constant strictly between 0 and 1/2, you also still get BPP. Okay, so as epsilon gets smaller, you're asking more and more of your randomized algorithm, but you can get it by just repeating a decent algorithm a few times and taking the majority results. Yep.
Do they have to sum to 1?
No, actually, it's enough that they be different by a little bit. So in fact, I wrote it symmetrically because it's a little bit natural that way. This says that it gives the wrong answer with probability at most epsilon. But actually, even if you put, for some reason, 0.8 and 0.7 here, greater than 0.8 or less than 0.7, you actually still get BPP. You can think about that. Basically you're getting out. In that case, you have an algorithm that gives you some signal about whether x is in the language or not, a signal 1 or 0, and like the signal is biased towards 1 more when x is in the language. Like the signal is 0.8 of the time it's 1 when it's in the language, and only 0.7 of the time is it in the language when it's not in the language, it's 1 only with probability 0.7. So you can repeat the algorithm many times, and if you see more than 75% ones, you'll guess that it's in the language, and if you see less than 75% ones, you'll guess that it's not in the language. Yeah?
So this is like stronger than saying it's just BPP. We're saying that it doesn't actually change it only changes constant factors.
Yes, as long as epsilon is a constant fixed in advance, then it only changes the running time by a constant factor, and so like it doesn't change BP time either, because BP time has a big O built in. Yeah. But you can even, and we'll do this, like talking about like epsilon, which is a function of n, and then it might change BP time by a function of n. Okay, what if you really get demanding? This is 99% at 1%. That's like you have a probability of 1% of making an error. What if you get really demanding and want no error? So you change this to, if it's in the language, you should accept with probability 1. And if it's not in the language, you should accept with probability 0. Which complexity class does this give? P, right. Yeah. So that's, you can think of P as a weird probabilistic complexity class. So algorithms of this type are said to have two-sided error because both in the case when x is in the language and when x is not in the language, they might give you the wrong answer. It's actually extremely common in randomized algorithms to have only one-sided error, which has the property that like, maybe if x is not in the language, you'll never make a mistake, but you might make a mistake when x is in the language by reporting that it's not, you're guessing that it's not in the language. As I said, this is actually extremely common in practice. So, for example, say you have an algorithm that accepts with probability at least 2/3 when the string is in the language, and when it's not in the language, it never accepts. That's quite common. It's called the one-sided error situation. That's like no false negatives or something. This defines a different complexity class called RP. Okay, so P stands for polynomial time, R stands for randomized. As always, these are poorly named. So that's a stronger property to have. It's not as good as zero error, but it's better than two-sided error. So this RP is, as we'll see in a second, maybe I'll just write it over here as we go along. It's a very popular randomized class, and it's bigger than P and smaller than BPP. And in fact, again, by the error reduction technique, it's actually easier. It's just enough that you have an algorithm that succeeds a little bit, as long as you have zero-sided, zero error in the no case. So again, this is for any constant epsilon greater than 0. This also gives you RP. I'll review this later in the lecture. Okay, I want to add 2 more rows to this table. So this is like, for any fixed constant epsilon, like 1%, if you're supposed to accept with probability at least 1% when it's in the language and always reject when it's not in the language. That's RP. What if you get like really weak and just say greater than 0 when it's in the language and equals 0 when it's not in the language? What complexity class does this give? NP, yeah. This is another way you can define NP. So really, a non-deterministic Turing machine is actually sort of the same as a probabilistic Turing machine. Like at each step, it can, have one of 2 possible things that it does. And, NP is just, it's like it's just about how you judge whether or not the algorithm has succeeded or overall accepted. And in this probabilistic viewpoint, you'd say that a non-deterministic algorithm succeeds or overall success if it's possible for it to make some non-deterministic or probabilistic choices that lead it to accept. Okay, so that you say it's in NP if, for every string in the language, there's like a positive chance that like it's non-deterministic, aka probabilistic choices lead it to accept. And when X is not in the language, then no matter what happens with these non-deterministic or probabilistic choices, it doesn't accept. Okay, finally, there's one more setting of these parameters which looks pretty natural, and maybe it might have even been like a person's first guess for how to define nice probabilistic complexity classes. Actually, it was defined kind of contemporaneously with BPP in the late 70s. And that's just like, I don't know, like greater than a half and less than or equal to a half. You have to make some like slight asymmetry choice here. I mean, you can't have greater than or equal to half and less than or equal to half, but so you say the algorithm succeeds if it's probably strictly better than a half, it rejects. Otherwise, you say it rejects. And this defines a complexity class, a quirky complexity class called PP. It's probabilistic polynomial time. And it's a quirky class. We will study it a little bit, but it's not the best definition from a practical point of view of things that can be solved efficiently in polynomial time. And as we'll see, the trouble is that like we don't have error reduction, very effective error reduction for PP. So it could be that you have a randomized algorithm that when the string is in the language, it accepts with probably a half plus 2 to the minus n. And when it's not in the language, it accepts with probably a half. So like barely any difference between the two possibilities. And it feels like there's no real way that you're getting like a lot of advantage out of knowing, having this very slight difference. But still, it's an interesting class, so we'll keep it in mind. Now that we actually have these rows here, you can see just by comparing these two rows that RP is contained in NP. Okay, if you have an RP algorithm, and you certainly have an NP algorithm, the relationship between the complexity classes BPP and NP is unknown. Either one of them, in principle, could contain the other. As I mentioned in the first lecture, it's sort of believed that BPP equals P, so therefore we sort of believe that BPP is contained in NP, but that's a sort of belief, and we don't really know anything. And to put the last complexity class PP into this map, well, it's clear that BPP is a subset of PP. If you have an algorithm that has two-sided error, this is also a two-sided error class, but if you have an algorithm with two-sided error, but like, its error is like a smallish number, like a quarter, then in particular you have a two-sided error algorithm whose error is strictly less than a half, but not the other way around. And it's also the case, and I'll prove it to you just in one line, that NP is a subset of PP. So one thing that's true about PP is that it's a not too big complexity class that contains BPP and NP. So it's a class that's like an upper bound on these two, as far as we know, incomparable classes, BPP and NP. This is a tangent, but it also happens to be the case that it's like the smallest natural class we know of that contains algorithms solvable efficiently by quantum computers. So it's like the smallest kind of classical upper bound on the power of quantum computation, PP. So let me prove this little star fact, just to kind of warm you up a little. Does anyone have a suggestion on how to prove it? Yeah?
Run it and flip a coin, and then so if you accept, then accept in the running part, and then if you reject, then flip a coin, and or there's some details, but you flip a coin, and the coin flip gives you the +1/2 to the greater than 0 and equals 0.
Yeah. I'll write what I think you intended here. Basically, it's like you have this. You kind of want to add a half. If you kind of add half probability to both of these things, then you kind of have it matching up. Let me write out a proof that will use some phraseology that I hope you get used to. So we want to show that NP is contained in PP, so we should really say, oh, let L be a language in NP. Let's show that it's also in PP. Well, to say that L is an NP is to say that there's a polynomial time non-deterministic Turing machine that accepts L in the sense of NP. So this is how, like, I think a complexity theorist would start to write this proof. They would say, let M be an NP machine deciding, well, that's it. Let M be an NP machine. Now, let me say what this means. It's a bit of a misnomer, but they're saying let M be a Turing machine. And to say that it's like an NP machine is to say that you should think of it as a non-deterministic Turing machine, and you should think of it as deciding a language according to the NP criterion. Okay, so deciding a language by this kind of funny criterion that NP has, where like if there exists non-deterministic choices which make the machine enter accept state, then you accept the string overall. Otherwise, if all the non-deterministic choices make the machine enter a reject state, you kind of overall reject the string. So you'll also hear like, things like, oh, let M be a BPP machine. And it's a bit of a misnomer, but like it really means let M be a probabilistic Turing machine where we like judge what language is decided by M according to like this criterion. So like let M be a machine with the property that for every X, the machine either accepts it with probability at least 2/3 or at most 1/3. And think of M as deciding a language according to this criterion. So like here, you can also think of M as like a probabilistic Turing machine. As I said, you can define NP in terms of probabilistic Turing machines. And like this phrase signals that like, but think of it as deciding a language according to this row. And then I would continue this kind of complexity theory way of phrasing the proof as follows. The following PP machine decides or defines the same language. So I'll call this PP machine M prime. And on input X, so what is it trying to do? In some sense, it's trying to, it's a randomized machine that's trying to judge if X is in the language. It sort of just wants to, if M accepts X with like any probability, then M prime should try to accept it with probability at least 1/2. And if M sort of always rejects X, then M prime should accept X with probability at most 1/2. That's what we need to do. And so just the idea is just like first step of the algorithm is flip a fair coin. And if it's heads, just immediately accept. Else, simulate M of X and do what it does. I mean, the idea being that you can think of M as a randomized Turing machine too. Right, so this M prime of X will have the property, just, visibly that like, for every string X, it's always accepting with at least 1/2, because the very first thing it does is accept with probability 1/2. But, beyond that, it accepts with probability strictly more than 1/2, if and only if M of X accepts with probability strictly more than 0. So it satisfies this criterion. Does that make sense? It's sort of explained in a slightly funny way, but this is some terminology that I guess you need to eventually get used to. Yeah.
If it required less than 1/2 for PP, would that change anything?
No, I'll mention that later. It's very, very annoying that like this is not like totally 100% symmetric. It's like so close to symmetric. But as I'll mention, and you can think about it as I'm talking until I come up to it. If we put greater than and less than here, 1/2, you would also get PP. Yeah. Actually, I'm going to talk about that quite soon.
What about the strict, do we know that some of those classes is a strict subset?
Nope. So let me add one thing here, and then that fact will become clear. PP is like some weirdo class, right? I didn't tell you much about it yet, and we might want to upper bound it by some class that we've heard of. So you can upper bound it by X, but you can also upper bound it by B space. Okay, so let's see why that's true. Let's say you have a machine M, and for every string x, well, you can tell if you think of that M as a PP machine, you can tell if in the language it decides x is in the language or not in the language by seeing if the machine accepts with probability strictly bigger than a half or at most a half. And I'd like to say that you can make that judgment in P space. How do you do it? Well, the P space machine just takes the input x and simulates the PP machine on x for every possible choice of the coin flips. So it runs the machine again and again on every possible sequence of random bits that it might use. And of course, it reuses space for each run. So it tries the all zeros random string, and then the all zeros except ending at one random string, and it reuses all the space. So the machine is polynomial time, so it never uses more than polynomial space. So you can do all these runs in polynomial space. You can count a counter of how many times the machine accepted. There are exponentially many different random strings that could be used, but that's okay. The counter will only take log of exponentially many bits to write down, so it'll only take polynomially many bits to write down. So you just count them all up and see at the end if is it bigger than half of all the runs or at most a half of all the runs. So that is the justification for why PP is in P space. So all these classes are sitting somewhere between P and P space. And it's a sad fact of life that as far as we know, P could equal P space. We certainly don't believe it, but it's possible. And therefore, we don't know that any of these inclusions is strict. Because even the outside one might not be strict. And as usual, not as usual actually. So we believe that, RP, NP, PP, and P space are all different. But actually, as I mentioned, the majority opinion is that BPP equals P. And so therefore, it also equals RP. But we don't know how to prove that. And I'll show you later an example of a problem that we know is in, let's say, BPP, but we don't know for sure is in P. OK. Any questions? OK, let me remind you of yet another complexity terminology, bit of terminology that I guess you've seen before, which is co. So recall or learn that co-C, if C is a complexity class, is a very simple concept. It's the class of all languages which are complements of languages in C. So C is any class. If you have a language, co-C is all the languages whose complements are in C. OK, so in some sense, whenever you have a class defined by, Turing machines, accepting and rejecting, if you just reverse the role of accept and reject, you kind of get the co version of the class. So we can apply this observation to all these classes and generate 2 new classes. So for example, co-P is P. Okay, you can see that this is symmetric, but I guess another way to see it is if you have a normal deterministic algorithm deciding a language, you can also, in polynomial time, or the same amount of time, decide the complement of the language. Just switch your notion of accepting or rejecting. But of course, that's something that you cannot do for NP, because the definition of NP is asymmetric between accept and reject. So co-NP, a class I hope you've seen before, at least the name of it, is a different class than NP. It's the class where there's a polynomial time algorithm that if you're not in the language, then you always reject. Wait, no, if you're in the language, let's see if I get this right. Yeah. Well, okay. So it's in co-NP. Also in co-NP means that you have some non-deterministic Turing machine that runs in polynomial time. So let's see, if x is in the language, then m of x has always accepts, and if x is not in the language, then m of x rejects for at least some choices of the bits. Okay. Okay, so what about co-BPP? This one is just the same as BPP, so we have not gained anything new. Well, that's because the definition of BPP is symmetric. Like if you just take a BPP machine and reverse its accept and reject states, then that will decide the complement language in this sense. Yeah?
For co-NP, I was wondering if you meant that we don't know if they're equal, or that they're explicitly not.
Oh, yeah. Like we don't know. Again, co-NP is somewhere in P space, so it's between them. So they could be equal, co-NP and NP as far as we know, but we very much believe that they're not equal. Okay, but conversely, let's do like a non-example. Co-RP is kind of like a real class in the sense that it's not equal to RP. This is like, again, RP has a non-symmetric definition. Okay, so like co-RP is kind of like, I'll mention this again in a second, but like it's got one-sided error, but in the other side, I mean, it could have, has no false negatives, but it could have false positives. Finally, what about PP? So this addresses your question. So this definition does not look exactly symmetric, and therefore it seems that it could be that co-PP is different from PP, but actually it's the same. And it's because of the reason that I wrote on the board here that if you make a symmetric looking but slightly different definition, this is like the most annoying thing about PP, but if you make the symmetric looking but slightly different definition that has to have like a strictly greater than a half chance of accepting in the yes case and a strictly less than a half chance accepting in the no case, you get the same class PP. And to show that, well, does anybody want to suggest how to prove that? Yeah?
Because you can use a similar error reduction technique, and it doesn't give you a bound on the error, but does like prevent it from being equal to 1/2 or something.
Yeah, you can like a little bit, yeah. Like you can do like a very slight error reduction that's like not very good, but like it's enough to make this a little bit less than 1/2. So, in order to show that this gives an equivalent definition, you have to show that if you have an algorithm with this kind of behavior, you can improve it a little so that it rejects with probably strictly less than 1/2 rather than just at most 1/2. How can you do that? Well, let's say your algorithm runs in time n squared. Your PP algorithm that achieves this runs in time n squared. Actually, that's not important. It's some polynomial time. Anyway, what you can do is take your PP algorithm, and the first thing you can do is flip n to the 10 coins, which is polynomial time. And if they all come up heads, then reject. Okay? And that will it'll like change. It'll slightly push both of these probabilities down by something like 2 to the minus n to the 10. So that's good in the sense that, I guess I did need the bound on the running time. That's good in the sense that it like pushes this less than or equal to 1/2 down to strictly less than 1/2. You might worry that like it pushes, your acceptance probability in some cases down below 1/2, which would be bad. But if the PP machine runs in time, let's say n squared, then it can only flip n squared coins, so like the probability of it doing everything is always an integer multiple of 2 to the minus n squared. So like if it's strictly greater than 1/2, if it has a strictly greater than 1/2 chance of accepting a string, then in fact it has a probability that's at least 1/2 plus 2 to the minus n squared. So by like, flipping more than n squared coins, like n to the 10 coins, you push all the probabilities down like a tiny fraction. It's not going to bother you in this case. Like you'll go down from 1/2 plus 2 to the minus n squared down to like that quantity minus 2 to the minus n to the 10th. It's still bigger than 1/2, but has the effect that it pushes this down to strictly less than 1/2. If you didn't get all that, like it's like a silly trick, but it's not too important. Do you have a question?
Why it pushes down the rejection probability? Because like if all coins has, then you reject, then it actually pushes the rejection.
Oh, sorry. Yeah, maybe you should accept. Yeah, I'm not really on my ball game today. Yeah, like if all, maybe you, you should probably, yeah, maybe accept because you want to push down the rejection probability.
Right.
It's not in the language you want to reject more often. So you don't
Yeah. So I was right, you're saying? Yeah, that's what I'm saying. It's annoying. It's one of these two things. Yeah. Yeah.
The confusion might be that they're both acceptance probability.
Yeah, these are both acceptance probabilities. So, right, you want to accept even less in this case. So you want to reject more. So you reject like at the beginning with probability 2 to the minus n to the 1/10th. Yeah.
So does that mean co-NP is also a subset of PP?
Yeah. That's right. So you can show that. Let me put that up here. You can show that. You can show that co-NP is a subset of PP directly by using a proof that looks like this. Probably just immediately rejects. Or another way to do it, and like this is like a trick to get used to, is we know that NP is contained in PP. Therefore, like it's immediate from the definitions that co-NP is contained in co-PP. And then you say, but co-PP equals PP, so therefore co-NP is contained in PP. So that's a common little argument that you see in complexity theory. If you have an inclusion, like you can take the co of both the classes, and then sometimes like you already know that one of the classes is closed under complement. So let's put the last ones into the picture. So I guess we also have co-RP. It has one-sided error, but in a different way. It looks like that, and like this. So it's also contained in BPP. So there's two different kinds of one-sided error. Co-NP and NP are also kind of like two different kinds of one-sided error, but like that error can be like enormous. It's just like you have some chance of getting the right answer in the good case. BPP is like two-sided error, but like a reasonable amount of error, which you can deal with. PP is like two-sided error, but just like with the barest, gap away from a half, which is not practical. Okay. Any other questions? Okay. There's one more class that one always brings up, which is ZPP. So, if you've never seen these things before, it's a lot of letters to digest. But there's one more class, ZPP. And that's the easiest way to define it is it's RP intersect co-NP. Sorry, co-RP. So it's things that have like an algorithm with no false, I wrote this down on my paper, an algorithm with no false positives and an algorithm with no false negatives. It's called, the Z stands for zero error. And that's because you can take this as like an exercise. It's also equivalent to languages L solvable with no error, like literally no mistakes at all, in expected polynomial time. Actually, let me just say in words why that is, because it might clarify a few things. So RP is sort of similar to NP. NP is like, when the string is in the language, there exists witnesses for that fact. The only trouble is like, they might be super rare from among the class of all potential witnesses. So like an efficient algorithm cannot like find a witness to the string being in the language itself. It needs like maybe a prover to give it the witness that certifies with the thing when the string is in the language. RP is kind of like the case where like plenty of strings are witnesses. So a deterministic algorithm might not be able to like deterministically find a witness to a string being in a language, but like if it just picks a potential witness at random, it has like a good chance of finding one, and then it can confirm that it is a witness or a proof itself. And conversely, co-RP is like co-NP is like when you have witnesses for certificates for strings not being in the language. So like the circuit unset problem is in co-NP, and that's because if you find a string that makes the circuit accept, that's a witness that you're not unsatisfiable. And co-RP is similarly like when there's plenty of witnesses for strings not being in the language, it's not obvious how to find them deterministically, but you can find them randomly. So ZPP is a situation where like both there are plenty of, like when it's in the language, there are plenty of strings that witness that it's in the language, and when it's not in the language, there's plenty of strings that witness that it's not in the language. So the algorithm that works is like you just keep picking strings that are potential witnesses one way or the other, check if they really are certificates for X being in the language, or the certificates that they're not in the language, and regardless of whether X is in the language or not, witnesses are aplenty in both cases. So like after just a expected constant number of tries, you'll find a witness to X either being in the language or not being in the language. So that's the idea behind that. Finally, one more comment I want to make about this. So that means that the picture is really like this. And right, these could all be the same. One more comment I said it before, is that in some sense BPP is like the class when you're like too lazy to figure out if your language has the no false positives or no false negatives property. Like it's just too annoying to remember what is false positive versus false negative, so you just say my algorithm has some error. But in real life, like every problem that we have an efficient randomized algorithm for, it seems that it has the property that it only errors on one side. It's always one-sided error, one way or the other. So in some sense, like RP and co-RP are like the classes that sort of really come up in practice, but like we still like BPP because it contains both of them. It's probably similar to them. You don't have to worry about what direction the error is going. Okay, so let me actually give you an example, because this will be motivating, and it's actually an important example in complexity theory of a language that we know is in BPP for sure, and we don't know is in P. So to illustrate that they might be different. And I won't go through in this full detail, but you can read a bit more about it in the textbook, and we'll come back to it later in the course. It's called the polynomial identity testing problem. And if you want to call it a language, people call it PIT usually. There's slightly different ways you can formulate it, but I'll just choose one here. So it's the language of all pairs of circuits, C1 and C2, but not Boolean circuits, arithmetic circuits. And I'll say what that is in a second. But basically, circuits that have plus and times and minus gates rather than and or. Over Z, the integers, computing the same function. So let me draw a picture. So an arithmetic circuit, like C1 is supposed to be, takes n inputs as usual and has one output as usual. But you think of the inputs xi as being, integers. And the gates are like times, plus, and minus. You can think of like allowing maybe the constant 1 also as a gate if you want. Okay, so C1 computes a function of its integer inputs. You can actually think of it as computing a polynomial in them. Because this will always produce a polynomial. And so you're given two suckers that look like this. And you want to know if they're actually computing the same function or not. And it's called polynomial identity testing because like this computes some polynomial, and this computes some polynomial, and you want to test if they're identically the same. So like you can take little polynomial identities like 1 plus x squared is 1 plus 2x plus x squared, and like that's a fact, but you could like design a circuit that first computes 1 plus x and then squares it, and then another one that computes the parts. And the task is to check that like an identity like this is true. Another way to think about this problem is like if you want, you can just like make one circuit that like subtracts the two of them, And then you're trying to ask, does this circuit output 0 for every input? So it's sometimes called zero testing. It's equivalent. So that's the problem. Given two circuits, compute the same function. And you can't just like kind of expand out what polynomial this computes, because it could have like a, this combination of pluses and times, which causes like the expanded form of the polynomial to have exponentially many terms. So you can't just like do that. I should mention that you can ask a similar question about Boolean circuits, and it's much harder. Like asking if two circuits are equal. It's basically similar to the SAT problem, because you could put like an XOR gate on top and ask, is this function computing like the identically zero function, or is there some inputs where it outputs 1, meaning the circuits differ? But it's easier in the arithmetic case. And as we'll see, it's in BPP, this problem. But on the other hand, it's not known to be in P. Okay, so I'll just tell you that. Nobody knows how to solve this problem in polynomial time. But you can solve it in probabilistic polynomial time. So I erased this panel to test your memory later. Yep.
Is there any intuitive explanation why this problem for arithmetic circuit is easier than for Boolean circuit?
Well, I'll tell you an efficient randomized algorithm now, and maybe that will give you some intuition. It's basically because polynomials are nicer. It's ultimately because if a polynomial is not identically zero, then it has to be non-zero on a large fraction of inputs. As we'll see. So here's the randomized algorithm for solving this problem. And I am not going to give you all the details of why this algorithm works. As I said, you can read about it in the textbook. Because I didn't have quite enough time to do all the details. But you should check it out. So it's in chapter 7.2.3 of Arora Barak. Okay, so here's the algorithm for solving this problem. Just let m be the size of C1 plus the size of C2, so the number of gates in them in total. Of course, there's a number that's no bigger than the input size. And actually, let me call the inputs x1 through xl. Normally, like, I don't know, you typically write n for the number of inputs, but I want to be a little bit careful. So like, n, I guess, is the bit complexity of writing down the description of these two circuits, like it always is. But they have L inputs and M gates. And I'm just going to use the fact that like L and M are both no more than the bit complexity of the inputs. Okay, so here's the algorithm, and here's the random part. Just pick random inputs. The basic idea is like pick a random input, evaluate both circuits on it, and if you get the same result, just guess that C1 is identical to C2 or computes the same function as C2. And if you get different results, then you know for sure that C1 and C2 don't compute the same function. There's slight twists on this idea, but that's the basic idea. So, randomly pick L, x1 through xl inside a big set of numbers. So you need to make this a bit bigger than 2 to the m, uniformly and independently. So here you use your randomness, and you use L times m plus 1 bits to write down these integers. So that's fine. And then compute. And I'll put a little question mark here, but we'll come back to that. Compute, as I said, the circuit's values on these randomly chosen inputs, the same ones, of course. And accept if and only if you get the same answer. Of course, if they really are computing the same function, then you'll certainly get the same answer. If they're computing different functions, you may or may not get the same answer. So that's something we have to concern ourselves with. But I suppose I should come back to this question mark because there's a bit of a difficulty with it. Can somebody say what the difficulty is? Yeah?
The output could be really big.
Right. So the inputs here are m bits long, and m is smaller than n, our input length, so that's fine. And whenever you add a couple of m-bit numbers, you'll get like an n plus 1 bit number, so it's no big deal. But when you multiply, you can get numbers that are noticeably bigger. And these could have linear depth, so you could have tons of multiplications in a row. So if you just do the naive thing, the answer, c applied to these things, could be exponentially larger than the inputs, and you don't even have enough time to write down the answer. So that's a shame. But you do a trick. You compute them mod 2 to the 2m. Okay, so if the number gets too big on you, you're just well, I'll reduce it mod 2 to the 2m. And now you can do this whole algorithm in polynomial time, because you're only ever keeping around numbers that have at most 2m bits in them. And okay, so let me write some facts. Fact 1, this is a polytime algorithm. On every input, it takes at most polynomial time. We just argued that. And fact 2 is the easy fact. If L is in pi, well, x is not a great letter, but if the input, C1, C2 is in the language PIT, and the probability that the algorithm accepts, this is over the choice of x1 through xl, that's the randomness the algorithm uses, is 1. Okay, because if they really are identical, then of course it'll get the same results. Okay, and fact 3 is the non-trivial part, and you can read this chapter to find out why it's true. But I'll just tell you, using an important but basic fact about polynomials called the Schwartz-Zippel lemma, Zippel, which basically says if you have a bounded degree multivariate polynomial, which is not the identically zero polynomial, then it's sort of often non-zero on a random input. Using this fact, you can show that if C1, C2, the input is not in the language, then the probability that the algorithm accepts is at most 1 minus 1 over 4m. So a little bit less than 1. So it has at least a 1 over 4m chance of picking numbers x1 through xl, such that when you do these two computations, mod 2 to the 2m, you get different answers. So a quiz question for you. Once you accept facts 1, 2, and 3, we immediately know that PIT is in what complexity class? Co-NP, very good. It's definitely in co-NP. So just by virtue of the fact that this is 1 and this is strictly less than 1, that means it's in co-NP. In other words, there exist witnesses that C1, C2 are not in the language. That's the co-NP thing, right? The NP thing is there exist witnesses that the input is in the language. And of course, these witnesses are these numbers that make the circuits output different things. But it's a bit better, and this gives me an opportunity to talk a bit more about error reduction, because it's not like this is just barely less than 1. It's actually less than 1 by a somewhat noticeable amount. It doesn't look great because it's 1 over 4m, but m is at most n. But it is great, actually. This is bounded away from 1 by an inverse polynomial amount. And it's not hard to do error reduction to improve this greatly. So in fact, this implies that we're going to get that PIT is in co-RP, and therefore BPP if you like. You're too lazy to remember the difference between co-RP and RP, by error reduction. Okay, so let me explain that. And it's sort of the obvious thing, right? You have this algorithm that it picks like a random potential witness to the fact that these two circuits are different. And occasionally, if they really are different, occasionally you get lucky and you find a witness. So you just repeatedly do this a bunch of times, and that will boost your probability of finding a witness when one exists. OK, so if you just repeat the whole algorithm, let's say 8m times. OK, so that adds a factor of order m to your running time, but that's OK. That keeps your algorithm polynomial time. Then what do? You do that, and then you sort of overall accept if and only if all runs accepted. So that's the overall algorithm. Then what happens? Of course, if it really is in the language, you'll just always accept, so you'll overall accept. And if it's not in the language, then the probability that you'll like overall accept, well, these are independent runs, so it's at most 1 minus 1 over 4m to the 8m. This is very small. I'll use my favorite fact in the world, that 1 minus u is less than or equal to e to the minus u. That's a great fact. You should always use it in life. So therefore, this is at most e to the minus 1 over 4m to the 8m. And that's e to the minus 2, which is less than 1/3, for example. And so now we have an algorithm that when this thing is in the language, you always accept. And when it's not in the language, you accept with probably at most 1/3. So that puts it into co-RP by our original definition. Any questions about that? Yeah.
If there's just one input to the polynomial,
Yeah.
does that make it any easier, or does it still seems to?
Oh, like the number of inputs is 1?
Yeah.
I should know this.
Well, just a univariate polynomial to some degree, and it has at most that many roots.
Yeah, it's an exponential degree.
Yeah. You're asking if it's in P, right? I should know this, but it's not occurring to me. So I guess I'll have to get back to you, unless somebody else knows.
So I think if you reduce it mod p, you should be able to identify it. Because like mod p, you can easily find the roots of the polynomial.
Yeah.
I don't know for sure, it's just like this.
Let me think about it. OK, good. So, or somebody just Google univariate polynomial identity testing and report the result to me. OK, let me spend 5 seconds on. We don't have the polynomial explicitly, but you have it somewhat. Like you might be able to compute its derivative implicitly given the circuit representation. So maybe. Let me think about it. OK, let me say a few things about error reduction. So briefly, generally, say you had, in this scenario, 1 versus at most 1 minus epsilon. So here epsilon was 1 over 4m. If you repeat 1 over epsilon times ln 1 over delta times, then it improves to, well, so 1 versus, and then we'll do that same e to the minus trick. So the epsilons kind of cancel. You get e to the minus ln 1 over delta. You get 1 versus delta. And so let's take a look at this. It's mildly costly to get, to worry about epsilon. So like, what this means is epsilon equals 1. Let's say you're trying to stay in polynomial time. Epsilon being 1 over poly n is OK. But actually, it's not very costly to get delta really, really small. So like you can have delta be 2 to the minus poly n, OK. And what I mean by OK is that, still polynomial time. Okay, so as soon as, let's say in the context of co-RP, you have an algorithm that succeeds, that rejects with probability 1 minus 1 over n to the 10, in the no case, then at polynomial expense, you can improve this to 2 to the minus n to the 10. Okay, so get like extremely good chance of success. Okay, so, right, so in RP, that 1 versus some number, which we initially fixed to be 1/3, it's equivalent if that 1/3 is anything between, inverse polynomial. Well, OK, yeah. Like this can be inverse polynomial, or this whole thing can be inverse exponential. And BPP is similar. It's a little bit more tricky when you have two-sided error. But in the interest of time, I'm not going to go into it. You just need Chernoff bound, which perhaps you've heard of before, to analyze the situation. So in BPP, it's similar. So say you had like x in the language implies probability of accept at least half plus epsilon. And x not in the language implies the probability of accept is at most half minus epsilon. And think of epsilon as small, but you want to amplify this. So the algorithm you'll do is repeat many times and take the majority answer that you get. And it's almost the same. If you use, let's say, Chernoff bound, you really can prove this elementarily if you want as well. If you repeat this order 1 over epsilon squared, that's the only downside, but it's not a big one, log 1 over delta times, and take the majority answer, you improve this above situation to 1 minus delta versus delta. So again, it's OK to have epsilon be 1 over poly n, and desire delta to be 2 to the minus poly n. But you see in both cases, like it's not OK if you're trying to stay within polynomial time for epsilon to be exponentially small. Okay? And that's why, like, if you have a polynomial time algorithm, then as I said, every probability involved is going to be some integer over 2 to poly n. So like if epsilon is strictly bigger than 0, then it's going to be something like 2 to the minus poly n. But that's too small to have good error amplification. So that's why like co-NP is not suddenly equal to co-RP. If you just have like strictly less than 1, it's like not enough of a gap to amplify it by repetition. And similarly, the fact that this only works for epsilon down to 1 over poly n is why PP is not the same as BPP. PP is like when this gap can be as small as exponentially small. And there, if you're only going to repeat your algorithm polynomial times, you just cannot get enough of like a good signal from your probabilistic algorithm that only has like a slightly better than half chance of success to really get like to the situation where you can like noticeably tell the difference between strings in the language and strings not in the language. Any questions about this? This is something like when I first learned this, I like couldn't remember easily, which is that there's an asymmetry here too, right? So like you can boost from a half plus 1 over poly all the way up to 1 minus exponential, but you cannot boost like from a half plus something exponentially small up to anything good in polynomial time. Okay, so this fact is very useful in the context of BPP. And often when you're studying BPP, or like a problem that's in BPP, or like you're talking about BPP, like the very first thing you should do is just say, let's assume immediately that I've done some error reduction so that instead of having at most 1/3 chance of error, I've got it down to some exponentially small chance of error. You can always do that without loss of generality, and it will like often make your subsequent argumentation a lot simpler. So, what we've seen out of this is that, if you have a language L in BPP, It implies there exists, a poly-time probabilistic Turing machine M with the following property. The probability, so for all x, the probability, and we say over R, the random coins that it uses, that M of x R is wrong. It gives the wrong answer, and this is vis-a-vis whether x is in L or not, is at most, you can put 2 to the minus n squared here. Let's say, let me just introduce the notation. Length of x is n. I'll put 4 to the minus n here. Okay, I won't even get that greedy. 4 to the minus n. Okay, so whenever you have a language in L and BPP, you can get this kind of fact. Okay, at the expense of maybe increasing the running time by order n. And let me just, so we have some more notation here, say this random string is randomly chosen from, well, some polynomial number of bits. Okay, so the running time of M here is polynomial, so P is some polynomial. It only has time to use polynomially many random coins. Okay, and in this notation here, think of M as a deterministic machine that takes X as the real input and R as a random string. Okay, so does everybody understand what this means and agree with it? The reason I emphasize this and why I chose this particular value is this is great because it's such a small probability of error that you can afford to do a trick, which is union bounding, in some contexts, over all possible strings x of length 2 to the n. All possible strings of length n. And your machine has only a small chance of making a mistake on any of those. So let me, you'll see what I mean when I prove this theorem that I mentioned last time, which is, I guess, probably what we'll end on. This theorem is that the complexity class BPP is contained in the complexity class P/poly. So this is efficient, randomized Turing machines. They have a good gap between their two error bounds, so like a small chance of error. This is languages with polynomial-sized circuit families. So we don't know that BPP is contained in P. In fact, we know this polynomial time identity testing problem that it's in BPP for sure. We don't know if it's in P. We kind of think they're the same, but BPP and P, but we can't prove it. But we do know for sure that if you allow non-uniformity, if you allow circuits, so like a different polynomial time circuit for every input length, then in fact, BPP is in this class. So you can trade, I guess, randomness for non-uniformity. So anything you could solve with an efficient randomized algorithm, there's at least a polynomial-sized circuit family for it. And we're going to prove this not using the notion of circuits, but using the concept of advice from last time that explained this /poly notation. So a polynomial time algorithm that takes a polynomial length trusted advice string. You can do it with circuits, but it's just slightly nicer to prove it with the advice definition. So what's the idea of the proof? Well, what do we have to do? Let L be in BPP. We have to show that it's in P/poly. Okay, so we'll just say, so star holds. Okay, so what is star? We have this great deterministic algorithm n that takes as input x, and it also wants to take as input a random string of length polynomial in length of x. And it gives you the correct answer about whether or not x is in L with extremely high probability over the choice of the random string. And in some sense, we want to make a deterministic algorithm, because we're shooting for a deterministic algorithm over here too. Can't somehow completely de-randomize it, but we can de-randomize it through the use of advice. So what is the picture here? Imagine we fix an n, an input length, and let this be this cloud be all strings of length p of n. P of n is the number of coins that capital M likes to use on inputs of length n. So what is the star fact saying? It's saying for any particular string, let's say the all zeros string, of length n. It's only an extremely small fraction of strings in here which, when used as R, give the wrong answer. So out of all these strings, only some very small fraction of them, this is the 4 to the minus n fraction of random strings R, which cause M to give the wrong answer on x equals all zeros. Okay, so almost all random strings, when x is all zeros, M will give the right answer. Okay, and there's some potential other, like 4 to the minus n, or at most 4 to the minus n fraction of random strings, which cause M to give the wrong answer on x equals 0, 0, 0, 1. And then you could do this for all the strings. So maybe there's some other bad random strings that are bad for 0, 0, 0, 0, 1, 0. But as I said, the point is you can union bound. So you can identify all the strings, random strings, which are bad for any input x of length n. And still they don't constitute a very large fraction of all the possible random strings. So union bounding over all x in 0, 1 to the n, what do we get? Well, at most, a 2 to the n, that's the number of strings we're union bounding over, times 4 to the minus n, that's the fraction of these random strings R that are bad for that string, which is still at most 2 to the minus n, which is much, much, much less than 1, fraction of random strings R are, let me say bad, let's say cause M to err on any x of length n. Okay, so when you're focusing on all the inputs of length n, for practically any random string R that you choose out of here, as long as they're not in these bad spots, that random R will be simultaneously good for all x's of length n, in the sense that you use that one fixed random string, and your randomized algorithm will give you the correct answer about x for every x. Okay, so it's like you just buy one book of random numbers of length n to the 10, and almost surely you can just use that fixed string as your random bits for your whole algorithm, and you'll get the right answer. So now we're actually extremely done, not just done, but very done, because for all n, right, there exists, in fact, many. In fact, the overwhelming majority of strings of this property, there exists many strings, let's say R sub n star, in 0, 1 to the p of n. But let's just say there exists one particular string, R star, such that we have this property. For all inputs of length n, M on real input x, and this magic string R star does the right thing. It accepts if and only if x is in L. So now this demonstrates that L is in P/poly, polynomial time with polynomial amount of advice, because this is our deterministic poly time algorithm. And these strings, R star 0, R star 1, etc., are the advice strings. And they're of polynomial length, so once you give a good advice string to M, it'll give you the right answer about everything in L. Yep?
What do you actually mean union bounding over all the x? Isn't the assumption that there is some advice, there's some string advice that you get to?
Yeah, you need that this, so it would have been fine if you got this down to 0.99, wait, let's see, 2 to the minus n times 0.99. That would have been fine. Because then When you union bound here, you'll get 2 to the n times this, which is less than or equal to 0.99, which is still less than 1. So like all we're trying to get at is there at least one good string, which is not in any of these splotches.
So if you just subtract -1, it will be fine as well, right? Like 2 to the minus n minus 1 also fine.
Yeah, it'll be even better, right? This will end up being a half or something. Yeah, so I put 4 to the minus n just for fun. So like, in fact, just to make the point that like you get into the situation where it's not even just like there barely exists one good string. In fact, practically every string is good simultaneously for every x. Yeah.
Does that help us, like having many good strings as advice in contrast to like only one?
Yeah, not for this proof, but we will use this fact later when we're studying BPP and interactive proofs and the polynomial time hierarchy. This fact that we get this like really excellent property where we can almost like invert the parameters, where like if you pick a random string, then with high probability it's simultaneously good for all x's. That's something we'll want to use. Okay, I had some more things to say. It's not critical for us to not say them, but let me just say them in words in 2 minutes without writing anything. So we introduced a bunch of complexity classes in this lecture, like BPP and RP and PP, and we also talked about P and NP. And there are 2 different types, and it gets to some question that was asked at the very beginning. Maybe I'll expand upon this in like Piazza or something. There's this informal terminology in complexity theory, in the sense that it doesn't have a totally official definition, but between syntactic classes, complexity classes, and here are some examples of syntactic classes, and semantic classes. And this lecture is a good one to bring it up because this is the first time we've encountered complexity classes that turn out to be quote-unquote semantic. Let me just briefly say in words what this means. The point of a syntactic class is that like as soon as I give you like a polynomial time probabilistic Turing machine, it for sure defines a language in PP. You take that machine and all the strings where it accepts with probability exceeding a half are in the language, and all the strings where it accepts with probability less than or equal to a half are not in the language. So like a polynomial time probabilistic machine automatically defines a language in PP. And similarly, a probabilistic polynomial time machine automatically defines a language in NP. Like all the strings where it accepts with probability strictly greater than 0 go into the language, and all the ones where it accepts with probability 0 are out of the language. And as soon as I give you a deterministic polynomial time Turing machine, it automatically defines the language in P. Like all the strings that accept go into the language, all the strings that reject don't go into the language. Semantic classes are the ones that like don't have this property. So like it's an issue that could happen. Like if I give you like a probabilistic polynomial time Turing machine, and let me add that like you can always be convinced that a Turing machine runs in polynomial time if I just like stick an alarm clock gadget onto it. Think about that. But anyway, if I give you a polynomial time probabilistic Turing machine, and you can easily become convinced it's polynomial time if I stick an alarm clock on it, it does not automatically define a language in BPP. It only defines a language in BPP if the machine has the following strange property. For every single, let's say this is M, it's a probabilistic polynomial time Turing machine, you want it to be the case that for literally every string x, either probability that M of x except is bigger than 2/3 or it's less than 1/3. If the machine has that property, then it defines a language in BPP. Namely, all the strings that make this true are in the language, all the strings that make this true are not in the language. However, it's not obvious whether a given machine has that property. In fact, it's undecidable. That's actually an easy exercise for you. If I give you a polynomial time Turing machine or a Turing machine that runs in n² time, for you to check whether or not this is the case, all strings have the property that like you either accept with probability at least 2/3 or at most 1/3. That's undecidable. So it's like not clear if a given machine defines a language in BPP or not. Similar for these cases. And that causes a lot of problems in complexity arguments because you cannot efficiently enumerate the BPP machines. So when we're proving the hierarchy theorem, time hierarchy theorem for P and NP, for example, like one component of it, which we didn't even think that much about, is that, okay, you can encode all the NP machines. But in some sense, you cannot easily like have an encoding of all the BPP machines, because like you can have an encoding of probabilistic Turing machines, and even of probabilistic Turing machines that have an alarm clock forcing them to halt in n squared steps. But there's no way to easily like check if they have this magical property. And for that reason, like there is no known time hierarchy theorem for BP time. And there's also no known BPP complete language. Again, for the same reason. For any syntactic class, you sort of automatically define a complete language for it. And I'm out of time, so I won't say, but I'll let you think about that. So these guys all have complete languages. We don't know any complete languages for these complexity classes. OK, so I'll see you on Thursday. And there is a homework 3 out.